Chapter 5 Helmholtz energy and Gibbs energy. Section 5.1 Definitions of Helmholtz energy and Gibbs energy. The Helmholtz free energy, or simply Helmholtz energy, is equal to the internal energy minus Ts. The Gibbs free energy is equal to enthalpy minus Ts. U and H differ by PV. H is PV plus U, therefore G and A also differ by PV. G is A plus PV. At constant temperature, the differential of the product of Ts is just TdS, and we know the Clausius inequality is this: TdS is greater than or equal to dQ. Using these two pieces of information, we can prove dA is less than or equal to dW. This is just because A is U minus Ts and du is dQ plus dW. And we can rearrange these three terms. We have dW and then minus TdS minus dQ. And again, TdS is greater than dQ or equal to dQ. So this value has to be non-negative. And dW minus a non-negative value is less than or equal to dW. We can also integrate this dA and this dW. We get delta A is less than or equal to W. That means the change of A, the change of the Helmholtz free energy, serves as the lower limit of W. At constant temperature, the increase in the Helmholtz energy of the system should be no more than the work done to the system. For example, if work of 5 joules is done to the system at constant temperature, then the Helmholtz energy of the system can increase by no more than 5 joules. At constant temperature, the decrease in the Helmholtz energy of the system should be no less than the work done by the system. If work of 5 joules is done by a system, that means this W is negative 5 joules. Delta A should be less than or equal to negative 5 joules. That means it's going to be more negative than negative 5. And in this case, the Helmholtz energy of the system decreases by no less than 5 joules. In both cases, delta A is the lower limit for work. Again, delta A is less than or equal to W when temperature is held constant. Because A is a state function, we know the cyclic integral of dA is 0. And then we can evaluate the cyclic integral of both sides. We have this cyclic integral of W, dW, greater than or equal to 0 after the system undergoes a cyclic process and returns to its original state. And because the integral of du is the cyclic integral of du is always 0, because u is a state function and the cyclic integral of any state function is 0, we have the cyclic integral of dq is equal to negative cyclic integral of dw, and that's always less than 0 or equal to 0. At constant temperature, we have dA is less than or equal to dW, delta A is less than or equal to W. The change of A serves as the lower limit for work. Under constant temperature and volume condition, we have dW expansion equals 0, because when the volume is held constant, dV is 0, so dW expansion is simply 0. Now we just divide dW into two parts: expansion work, non-expansion work. If the condition is constant temperature and constant volume, dW expansion is 0, and because dA is less than or equal to dW, under constant temperature and volume condition, we can write dA is less than or equal to dW non-expansion, and therefore delta A is less than or equal to W non-expansion. The change of A serves as the lower limit of non-expansion work. For example, electric work is non-expansion work under the constant temperature and volume condition. Now we can prove this under constant temperature and pressure condition. The change of G serves as the lower limit of non-expansion work. Here's the derivation. If the temperature and pressure are both held constant, dG is dH minus TdS. It's just because G is defined to be H minus Ts. H is U plus PV, du is dq plus dw. dPV is actually PdV plus VdP in general, but in this case pressure is constant, so dPV is PdV. And since temperature is constant, dTs is TDS. And then we have this many terms. We can put dq and TDS together over here, and then we have dW and PdV. And over here we just swap the sign. It's negative TDS minus dq, and dW is non-expansion work plus expansion work, and then we have PdV. Now this expansion work is negative PdV, so negative PdV and PdV cancel. We have this three terms. If you look at the this number one term, number two term, TDS is always greater than or equal to dq based on Clausius inequality. So over here we have a non-negative number, and this with this negative sign, we know the sum of these terms should be less than or equal to dW non-expansion. Again, this is just because TDS is greater than dq for irreversible process. TDS is equal to dq for reversible processes. Now we just proved dg is less than or equal to dW non-expansion. The equal sign holds when the process is a reversible process. We can then integrate both sides. Delta G is less than or equal to non-expansion work under constant temperature and pressure condition. The change of G now serves as the lower limit of non-expansion work when temperature and pressure are constant. At constant temperature and pressure, delta G is less than or equal to non-expansion work. Therefore, the increase in the Gibbs energy of the system should be no more than the non-expansion work done to the system. Here's an example. If the electric work of 5 joules is done to a system at constant temperature and pressure, the Gibbs energy of the system increases by no more than 5 joules. At constant temperature and pressure condition, the decrease of the Gibbs energy of the system should be no less than the non-expansion work done by the system. So if the system does electric work of 5 joules under constant temperature and pressure condition, the Gibbs energy of the system decreases by no more than 5 joules. For example, it can be 6 joules. Therefore, under constant TP condition, electric work of more than 5 joules must be done to a cell phone battery to increase its Gibbs energy by 5 joules. The battery can provide electric work of less than 5 joules when its Gibbs energy decreases by 5 joules. This is just because electric energy is partially wasted in the form of heat when you are charging or using the battery. Either way, part of the electric energy is wasted. After a cyclic process of charging and discharging, delta G should be 0. So the Gibbs energy of your cell phone battery should be unchanged after a cyclic process, because G is a state function. But W, non-expansion, this is non-expansion work, overall should be greater than 0 or equal to 0. The equal sign holds only for reversible processes. For irreversible processes, the non-expansion work is greater than 0, and then you know Q of the Q of the system should be less than 0. Heat is released to the surroundings. That increases the entropy of the surroundings, and overall it increases the entropy of the universe. So it's a irreversible process. Again, in an irreversible process, part of the electric work is wasted in the form of heat that's released to the surroundings, and that's why the battery gets warmer no matter you're charging it or using it. In summary, A and G are introduced in thermodynamics because delta A or delta G can serve as the lower limit for non-expansion work, such as electric work, under constant TV or constant TP conditions. Because chemical reactions and physical changes take place more often under constant TP conditions for safety and for convenience, so we often look at delta G. We often study delta G, calculate delta G as the lower limit for non-expansion work.